The first topic that I'm going to cover is linear algebra, and it's probably the most useful mathematical tool in all branches of science. Probably even more useful than the famous calculus. In any branch of maths, we need some objects to work with. For example, in high school algebra, objects are numbers, real numbers, or integers, or fractions. And after that, we need to define some operations to get new objects from existing objects. For example, we define addition, multiplication, or taking a square root of a number. In linear algebra and basically other fields of maths, we follow the same logic. First, we need to create some objects and then some operations. The first object in linear algebra is a vector. Simply, a vector is a list of numbers. This list can be as short as a single number or as long as a million numbers, or even more. But first of all, we need notation, a mathematical notation to show our objects. So we use a symbol and a bar on top of it to show a vector, and sometimes an arrow. And then we use numbers with square brackets. And we call each element of our vector an entry. To be more precise, each entry should have an address. So we start from top of the column, top of the vector, and we call the first entry with the same symbol as our vector, here x1, and then the second entry x2, and all the way down to the last entry, which we call xn. And n here is the number of entries of our vector. This is how we show a vector algebraically, but sometimes we can show them geometrically, specifically when number of entries is small. For example, if x has 2 entries, then we can show the vector in a 2D plane, where the first entry would be the first coordinate and the second entry would be the second coordinate. And the vector is shown by an arrow from the origin to the point that we reach by the entries as our coordinates. Similarly, a vector with 1 and 3 entries can be shown on a number line and in a 3-dimensional space respectively. Now we have created our object. It's time to define operations. The simplest operation on a vector is scalar multiplication. A scalar is simply a real number. Here alpha is our scalar, and we want to multiply it by a vector, here x. You probably know how we multiply a scalar by a vector. We just multiply each entry of the vector by that scalar. But what is the geometric interpretation of a scalar multiplication? It can be shown if our original vector is x, the alpha x would always lie along the x itself, sometimes shorter, sometimes longer, and sometimes in opposite direction. If alpha is bigger than 1, alpha x would be larger than x. If alpha is smaller than 1, alpha x would be shorter. And if alpha is negative, alpha x would be in opposite direction. But in any case, the scalar multiplication of a vector would lie on the extended line of the original vector. This statement can easily be proved by using similar triangles and using some theorems from Euclidean geometry, but here we skip the proof. The next operation is vector addition. Two vectors can be added to each other if they have the same number of entries. We simply add corresponding entries to each other. To geometrically add two vectors, we can use two equivalent methods. In the first method, we create a parallelogram by shifting vectors. We put the tail of the second vector on the tip of the first one, and also the tail of the first one at the tip of the second vector. And the resultant vector would be from the vertex of the parallelogram located in the origin to the opposite vector. In the second method, which is a shortcut of the first one, we put the tail of the second vector at the tip of the first one, and the resultant vector would be from the tail of the first one to the tip of the second one. The next operation is vector subtraction. This operation is in fact a combination of a scalar multiplication and addition. So subtracting v from x means we first multiply v by -1 and then add that vector to the vector x. The geometry of subtraction follows the same logic. We have x and v. So first we need to multiply -1 by v. We get the same vector but in opposite direction. And we use the parallelogram or the triangle method to add -v and x. So we get x minus v. The next operation is dot product, and it's probably the most important operation in linear algebra. It's also called inner product. To indicate this operation, we put a little dot between two vectors. Now let's see how to do this operation. This operation to be valid, two vectors must have the same number of entries. Here we have x and v with 5 entries. First we multiply corresponding entries of two vectors. We multiply x1 by v1, x2 by v2, x3 by v3, and all the way down to the last entry. And then we add all these numbers. We can demonstrate this operation in compact form by sigma notation. It is read as sum of multiplications of corresponding entries of two vectors. An important concept related to vectors is length of a vector. Given a two-dimensional vector or a vector with two entries, how can we get the length of that? The answer is we can build a right triangle. And because we know the sides of this triangle, we can compute the length of the hypotenuse, which is the length of our vector. We show the length of a vector with two vertical bars on each side of the symbol. And if you rearrange this equation, you can find out that the length of a vector is actually the square root of the dot product of a vector by itself. We have shown this in two-dimensional plane, but it is generalized to higher dimensions. So it doesn't matter how many entries our vector has. The length of a vector is always the square root of sum of the squares of entries. Now, what is the unit vector? A vector with length of 1 is a unit vector. This concept is important because unit vectors make equations simpler and computations easier. Given a vector v, how can we get a unit vector in the same direction? In other words, what is the corresponding unit vector of v? Here we call it w. From the previous section, we know that w is a scalar multiplication of v. So to solve this equation, we need to find the alpha. But we know the length of w, or alpha v equals 1. Then we can take out alpha from the length of formula. This is just the factorization. You can prove it for yourself. And then we can solve for alpha. Alpha equals 1 over the length of v. Substituting this in the first equation, we have reached to a formula to compute the unit vector corresponding to an arbitrary vector. So to compute the unit vector, we just divide each entry of a vector by the length of that vector. In two-dimensional space, all unit vectors lie on the unit circle. And in three-dimensional space, all unit vectors lie on the unit sphere. Now, let's talk about linear projection. Linear projection means casting shadow of a vector on a linear surface. And by casting shadow, we really mean it. Imagine that we have a vector in three-dimensional space. For example, in a box. And then we shine a light from one side of the box. And on the opposite side, we get the shadow of the vector. The length of this shadow depends on the length of the vector itself and also the angle between the wall and the vector. For example, you can imagine that if the vector is perpendicular to that side of the box, then this shadow would be a single point with length 0. Now let's be more precise. We have a vector u in two-dimensional plane, and we want to project it on another vector w, or the extended line of that vector. So we shine a light perpendicular to the vector that we want to project on, W, and we get the shadow. And we call it U projected. By looking at the geometry of projection, we can easily find out that U projected is actually a scalar multiplication of W. And to find U projected, we just need to find that scalar, here beta. It turns out that beta is dot product of U on W divided by the length of W squared. This fact can be proved in several ways, including using law of cosine, but I don't want to prove this here. So by substituting beta in the first equation, we can get a formula for computing U projected. Now we can use what we learned from linear projection to get an insight of the geometric interpretation of dot product, because dot product is a very important concept and operation in linear algebra. By using Pythagorean theorem, we can see that the length of U projected equals the length of U times the cosine of theta, where the theta is the angle between W and U. In the previous part, we found a formula for U projected. And if we rearrange that formula a little bit, we can see that a terms appear here that is actually a unit vector. So when we want to compute the length of U projected, we can ignore that part. And by substituting the left-hand side of this equation, we can reach to the next one. The length of U times cosine is just equal to dot product of U times W divided by the length of W. And we can multiply both sides by W and we get a formula for dot product. This formula is really useful because it says that the dot product of two vectors is just the length of the first vector times the length of the second vector times the cosine of the angle between them. Now, let's analyze this formula for a few cases. First, let two vectors be perpendicular. And because the cosine of 90 degree is 0, then the dot product would be 0. So when two vectors are perpendicular, the dot product is 0. In the second case, let two vectors lie on the same line and in the same direction. In this case, the cosine of 0, the angle between two vectors, is 1, and the formula reduces to multiplication of lengths of two vectors. In the third case, two vectors lie on the same line but in opposite direction. So the angle between two vectors is pi, or 180 degrees, and the cosine would be -1. And the dot product reduces to minus product of lengths of two vectors. In general, dot product is always bigger than minus the multiplication of lengths and always smaller than multiplication of lengths.